Here we have a type of turning point, a point where the gradient is 0, so dy dx is equal to 0. And this type of turning point is called a local maximum. It's the highest point of a curve in a particular region. Most people just refer to it as a maximum and give it the abbreviation max. We locate turning points by solving dy dx is equal to 0. We start with the original curve, differentiate to get dy dx, and set that expression equal to 0. This enables us to find the x-coordinates of turning points. But we also need to know the type of turning point. And there's two ways of analyzing our curve to find this. One is to use something called a sine table, and the other is to use the second derivative called d2y dx squared, which is what we get when we differentiate the dy dx expression again. If we consider first the sine table, a sine table looks like this. We put x values in the top, dy dx in the middle, and the bottom is left for a picture. We need 3 x values. The x-coordinate at which dy dx is actually equal to 0 is always put in the middle. We need to take an x-coordinate to the left of this, provided it does not go past another turning point, and put it in this box here. So we could put 1 here, for example. And then we want to point to the right under the same provision that this point does not go past another turning point. So here, in this example, we would have a turning point at 2. 1 is to the left and 3 is to the right, and there are no turning points between 1 and 3 other than our 1 at 2. Since the turning point is actually at 2, dy dx is 0 at this point. For a maximum, we have a positive gradient before 2, and we have a negative gradient after 2. Our picture would be positive gradient, 0 gradient, negative gradient, and we can see that this shape forms a local maximum. Let's look now at the second method, the second derivative d2y dx squared. d2y dx squared is the gradient function for dy dx. This follows since dy dx is the gradient function for y, so if we differentiate again, d2y dx squared is the gradient function for dy dx. If we consider what happens to dy dx here, it has a positive value, followed by 0, followed by negative. So if we plotted dy dx, it would go from positive through 0 to negative, and therefore has a negative gradient. So its gradient function would be negative. If we find that d2y dx squared is a negative value, this implies that we have